Hello and welcome to Cosmic Sleep Stories. Tonight, we'll drift into a tranquil journey through the cosmos and beyond, exploring 100 gentle, sleep-inducing facts that will carry you softly into the night. Imagine for a moment that you are floating gently downward, drifting past the surfaces of things you see every day, moving beyond what your eyes can perceive. The world around you begins to dissolve into something softer, something less solid than you ever imagined. At this smallest of scales, everything you thought was firm and real, the ground beneath you, the air you breathe, even the very fabric of your own being, is mostly emptiness, mostly space between tiny dancing points of light. Long ago, before telescopes and microscopes revealed the hidden architecture of existence, there lived a simple idea. Ancient thinkers in distant lands once dreamed of the tiniest pieces of the world, invisible fragments they called the uncuttable ones. These were imagined as eternal building blocks, unchanging and solid, the foundation beneath all the shifting forms of life and matter. It was a beautiful thought, born not from experiment, but from wonder and the human desire to find order in the ever-changing dance of nature. Yet these early visions were only whispers of truth. The particles they imagined were nothing like the mysterious entities that modern seekers of knowledge would eventually discover. Those ancient atoms were static, simple, and silent. They lacked the layers of wonder, the waves of possibility, the gentle mysteries that would one day be revealed when humanity learned to look closer, deeper, and with more patient eyes. As centuries drifted by like clouds across an endless sky, new tools emerged, new ways of seeing. Thinkers began to unravel what these tiny pieces truly are. Instead of solid spheres, they found mostly emptiness, vast open spaces filled with delicate particles moving in clouds of probability around dense centers. And these parts, these fragments of existence, do not behave like tiny stones or grains of sand. They move in ways that seem almost like dreams, sometimes appearing as particles, sometimes spreading out like gentle ripples on a silent pond. The journey from those ancient philosophical musings to the subtle understanding we hold today is a story of patience and curiosity. It teaches us that reality can be far more delicate, far more mysterious than our first impressions ever suggest. The atom, once thought to be the smallest indivisible piece of everything, turned out to be a doorway into a universe filled with uncertainty, with waves of chance, with profound beauty waiting quietly beneath the surface of all we think we know. In an era when science was beginning to take its modern shape, one thoughtful observer brought fresh clarity to the idea of these tiny building blocks. He proposed that everything we touch and see is made of minuscule particles, identical spheres of a given kind, that combine in fixed, predictable ways to form all the substances around us. This was a step forward, giving scientists a framework to explain how matter behaves, how it combines and separates in the quiet dance of chemical change. This vision suggested that the particles of a particular element were identical in their nature and distinct from the particles of other elements. He imagined them as solid, unbreakable spheres, each with its own identity. Chemical reactions, in this view, were simply rearrangements, these spheres coming together or drifting apart without ever breaking into smaller pieces. It was a simple picture, yet powerful enough to explain many mysteries, such as why water always forms from the same proportion of lighter and heavier invisible elements. Yet despite its elegance, This view had its limits. The tiny spheres were not, it turned out, indivisible after all. Later discoveries would reveal even smaller entities dwelling inside them, changing forever what it meant to speak of an atom. Still, this early model marked a crucial moment, a bridge between ancient dreams and modern science, transforming centuries of philosophical wonder into something that could be tested, measured, and refined. This shift from simplicity to complexity mirrors the unfolding mystery of the atom itself, moving from the image of solid, unchanging blocks toward the revelation of dynamic systems rich with unseen motion, vibrating with the gentle rhythms of uncertainty. As the understanding of matter deepened, new revelations emerged that challenged the notion of atoms as solid, indivisible units. Through careful experiments with streams of particles moving inside glass vessels emptied of air, one curious mind discovered something remarkable. The streams were made of particles far lighter than any known atom, tiny fragments carrying a negative charge. This was the first glimpse into the hidden interior of the atom, proof that it was not a simple, unbreakable sphere, but something with structure, with parts within parts. The discovery of these negatively charged particles, so much smaller than atoms themselves, raised new questions. If atoms contain negative charge, what balances it? How are these tiny pieces arranged inside? The investigator proposed a picture: the atom as a sphere filled with positive charge, with the negative particles scattered throughout like seeds in soft fruit. Though this image would later be replaced, it was an important step, showing that atoms have an inner architecture. Soon after, other hidden pieces were identified. Particles carrying positive charge were found, along with others that carried no charge at all, but contributed weight and substance. These discoveries revealed the atom as a miniature universe unto itself, a delicate system of charged entities interacting in invisible balance. This growing knowledge transformed the sciences of matter and energy, showing that even the building blocks of existence are themselves composed of parts. The atom was no longer a static object, but a dynamic system, a gentle mystery waiting to be understood more deeply. As the journey continues, these early findings would lead curious minds deeper still into a realm where particles behave in ways that defy everyday logic, where certainty gives way to clouds of possibility. Around the time when new ideas about atomic structure were first being tested, a bold experiment was designed to peer into the heart of matter. Researchers directed a stream of tiny charged particles toward an ultra-thin sheet of precious metal, expecting them to pass through mostly undisturbed, as if moving through soft mist. According to the prevailing picture, the positive charge inside atoms was thought to be spread out gently, allowing particles to drift through with little resistance. What happened instead was astonishing. While most of the particles did pass through with hardly any deflection, a small number were turned aside at steep angles. Some even bounced back toward the source, as if they had struck something incredibly small yet incredibly dense. This unexpected result suggested that the positive charge and nearly all the mass of the atom were concentrated in a tiny region at the center rather than spread throughout. A new vision emerged. The atom's positive charge and almost all its substance reside in a minuscule core, with the lighter negative particles moving in the vast open space around it, much like distant wanderers circling a central beacon. This picture overturned earlier models, and introduced a new way of understanding atomic structure. The atom, it turned out, is mostly emptiness, with a hidden dense heart at its center. This discovery was a turning point, marking the birth of a new era in the study of matter. It revealed that atoms have a core, a nucleus, and set the stage for the next great shift in understanding, one that would lead to the recognition that certainty and fixed paths do not govern the tiniest scales. Instead, a more subtle, probabilistic view was needed, one where particles exist as waves of possibility until observed, where the familiar rules of the visible world no longer hold sway. This glimpse into the atom's inner sanctum invites us to keep looking closer, to embrace the mystery and the beauty hidden within the smallest fragments of existence. Building on the revelation of the atomic nucleus, a new picture of atomic structure emerged. This vision proposed that the lighter particles do not simply drift randomly around the nucleus, but move in specific stable paths, somewhat like celestial bodies tracing their courses through space. This idea was revolutionary because it introduced the concept that energy within atoms comes in fixed, distinct amounts, rather than as a smooth continuum. The particles orbiting the nucleus could only occupy certain allowed paths without losing energy and spiraling inward. It was suggested that these particles jump between these fixed paths by absorbing or releasing discrete packets of energy. This explained the distinct patterns of light emitted or absorbed by different elements, patterns that had puzzled observers for years. Each line in these patterns corresponded to a specific transition between energy levels. While this model worked beautifully for the simplest atom, it struggled to explain the behavior of more complex ones. Nonetheless, it marked an important step toward a deeper understanding of nature's inner workings by blending older ideas with new principles. The image of particles circling the nucleus in neat paths provided a comforting visual, a way to imagine the invisible world inside matter. But the true nature of this quantum realm would prove to be far more mysterious and less easily pictured. Still, these insights paved the way for later developments, including the recognition that particles behave as waves and that their positions and motions are best described through probabilities rather than certainties. This model also hinted at a deeper principle, that nature's smallest parts do not follow smooth, continuous motions, but move in discrete steps governed by fundamental constants woven into the fabric of reality. This was a profound shift from earlier worldviews, inviting humanity to reconsider the very nature of matter and energy, to accept that the universe at its tiniest scales operates by rules far stranger and more subtle than everyday experience suggests. With this vision of the atom, the door to quantum understanding opened wider, beckoning explorers to venture into the strange, silent dance of particles at the heart of all things. This early picture of atomic structure was groundbreaking, yet it soon became clear that the older, familiar rules of motion and energy could not fully explain the strange behaviors observed at the smallest scales. As experiments delved deeper, scientists encountered phenomena that defied the familiar logic of everyday objects. One early puzzle involved light shining on certain metals and releasing tiny charged particles. Older wave theories of light predicted a gradual energy increase, yet experiments showed particles were only released when the light reached a certain frequency, suggesting that light behaved like discrete bundles of energy rather than a continuous wave. This insight helped launch a new way of thinking about energy and light. Around the same time, it was proposed that energy is not emitted or absorbed smoothly, but in fixed amounts, like steps on a staircase. This idea explained how hot objects radiate light, shattering the notion that energy changes were always smooth and continuous. Then came the unsettling realization that particles like the lighter ones, orbiting atomic nuclei, exhibited properties of both particles and waves. It was suggested that these particles have a wave-like nature, and experiments confirmed this, showing interference patterns typical of waves. This duality undermined the older picture of particles as tiny solid objects moving predictably through space. Further challenges arose with the recognition of fundamental limits on how precisely certain pairs of properties can be known at the same time. This uncertainty is not due to flaws in measurement, but is woven into the very fabric of nature itself. It revealed that the universe at its smallest scales has a built-in fuzziness, a gentle resistance to complete predictability. These developments culminated in the creation of a new framework, one describing probabilities and uncertainties rather than fixed paths and definite outcomes. The older physics gave way to a world where observation, chance, and mathematical functions representing possibilities govern the tiniest scales. This new quantum view unsettled many, for it challenged long-held beliefs about the clockwork precision of the universe. But it also opened a window into the deep structure of reality, inviting humanity to reconsider what it means to truly know the universe and to accept that at the heart of existence lies a dance of possibilities, soft and mysterious as a dream. Let us pause here and explore one of the most intriguing and fundamental truths about the quantum world. At the heart of this realm lies a surprising duality. Tiny entities like the lighter particles orbiting nuclei and the packets of light that carry energy do not fit neatly into the categories we use in everyday life. Sometimes they behave like particles, small and localized. Other times they act like waves, spreading out and interfering with themselves in patterns of light and dark. This dual nature was first glimpsed in experiments with light itself. For many generations, light was considered a wave, responsible for phenomena like the bending of light around corners and the patterns of brightness and shadow created when waves overlap. Yet certain experiments revealed that light also behaves like a stream of discrete energy packets, each carrying a specific amount of energy. The concept took a bold leap when it was proposed that not just light, but all matter, including the tiny particles within atoms, could exhibit wave-like properties. This idea was revolutionary, suggesting that particles might have an associated wavelength influencing how they move and interact. Experiments soon confirmed this duality. When tiny particles were fired through thin layers of matter, they produced interference patterns, signatures of wave behavior, something unimaginable if they were simply tiny solid spheres. This dual behavior challenges our everyday intuitions. How can something be both a particle and a wave? The answer lies in the probabilistic nature of the quantum realm. Instead of having definite positions and speeds, particles are described by mathematical expressions encoding the probabilities of finding them in various places. This dual behavior is not just a curiosity, but lies at the core of much modern technology, from devices that magnify tiny structures to the tools that power communication and computation. As we continue, we will explore how this duality shapes atomic structure and the mysterious rules governing the tiniest parts of reality, rules that whisper softly beneath the surface of all we see. One of the most striking demonstrations of this dual nature is an elegant experiment that has captivated curious minds for many generations. In this experiment, a stream of light, or even tiny particles, is directed toward a barrier containing two very narrow, closely spaced openings. Behind this barrier, a detection surface records where the light or particles arrive. If particles behaved like tiny solid objects, we would expect to see two bright spots on the detection surface, corresponding exactly to the two openings. But instead, what appears is a series of alternating bright and dark bands, known as an interference pattern. This pattern is a clear signature of wave behavior, created when waves overlap and interfere, amplifying in some places and cancelling out in others. What makes this experiment truly astonishing is what happens when particles are sent through the openings one at a time, slowly building up the pattern over time. Each particle arrives as a single point, like a localized object. Yet as more and more particles pass through, the interference pattern emerges, as if each particle somehow passed through both openings simultaneously and interfered with itself, behaving like a wave rather than a tiny sphere. When detectors are placed to observe which opening each particle passes through, this wave-like behavior disappears. Instead, particles behave as if they took one path or the other, and the interference pattern vanishes. This suggests that the very act of observation changes the nature of what is observed, a profound insight into the quantum world. This experiment forces us to rethink basic assumptions about reality. It reveals that at the quantum level, particles do not have definite paths or positions until they are measured. Instead, they exist as mathematical descriptions of probabilities spread over space. When measured, these probability waves collapse to a definite location. This elegant demonstration shattered older notions of certainty and showed that the universe at its smallest scales is far stranger and more mysterious than our everyday experience suggests. It reminds us that reality is not a simple, fixed stage, but a dance of possibilities, gentle and elusive as moonlight. In the quantum world, there are fundamental limits to what we can know simultaneously about certain properties of particles. This truth is captured in a principle of uncertainty, a cornerstone of quantum understanding. It tells us that the more precisely we try to measure where a particle is, the less precisely we can know how fast it is moving. And the reverse is also true. This is not due to flaws in our instruments or techniques, but is a fundamental property of nature itself. Imagine trying to pinpoint exactly where a tiny particle is located. The act of measuring its position with great accuracy inherently disturbs its motion, making it impossible to know both precisely at the same time. This is not just a technical limitation, but reflects the inherent fuzziness of particles at microscopic scales. This principle challenges older ideas where objects had definite, predictable positions and speeds. Instead, at the quantum level, particles behave in ways that resist exact description, embracing probability and a gentle uncertainty. It reminds us that reality is not a simple clockwork mechanism, but a dance of possibilities, soft and ever-shifting. This uncertainty has profound implications. It means that the universe itself has a built-in limit to predictability, setting a boundary for the exactness of measurement and knowledge. This uncertainty is not just theoretical. It influences how atoms bond, how particles interact, and underpins the stability of matter itself. Understanding these limits helps explain why the quantum world feels so strange and counterintuitive, yet also why it is so rich and full of surprising phenomena. It invites us to accept a universe where certainty is replaced by possibility, where the act of observation plays a central role in shaping what we know, and where the tiniest fragments of existence exist in a state of gentle, dreamlike ambiguity until we look closely. One of the most important tools for understanding the quantum world is a mathematical expression that describes how the state of a particle changes over time. Rather than picturing particles as tiny solid objects moving along fixed paths, this approach treats them as waves that spread out and interfere, creating patterns of probability. These probabilities are not just abstract ideas. They form what we call probability clouds, regions around an atom's nucleus where a particle is most likely to be found. Unlike the precise orbits in older models, these clouds give a soft, ever-changing shape to where particles can exist, reflecting the uncertainty and fluidity of the quantum realm. Instead of saying a particle is here at this exact point, quantum understanding tells us it is more accurate to say the particle has this likelihood of being here and another likelihood of being there. This mathematical tool helps calculate these likelihoods, revealing the complex and beautiful shapes that particles inhabit. This concept fundamentally changes how we understand the building blocks of matter. Atoms are not tiny solar systems with particles tracing fixed paths, but rather dynamic, probabilistic systems where particles blur in space, guided by the mathematics of waves and possibility. This approach connects the unseen quantum behavior with measurable properties, making it central to modern understanding of physics and the nature of matter. By imagining particles as probability clouds, we embrace a world where certainty gives way to possibility, a quiet dance of existence that defies everyday intuition, yet shapes everything we see around us. It is a vision of reality where the solid becomes soft, where fixed becomes fluid, and where the very act of looking changes what we find, like trying to grasp mist that slips through your fingers, beautiful and elusive. In quantum understanding, the idea of a quantum state is fundamental. It describes all the information we can know about a particle or system at a given moment. But unlike in older physics, where an object had a definite position or speed, a quantum state allows for something far more mysterious, the principle of existing in multiple possibilities at once. This principle means that a particle can exist in a blend of different locations or energies simultaneously, not one or the other, but both at once. It is only when we measure or observe the particle that this blend settles into a single outcome, like a coin spinning in the air that is neither heads nor tails until it lands. This concept challenges our everyday experience. We are used to things being in one place or having one property. But at the quantum scale, particles seem to hold several possibilities together, woven into a single state, as if reality itself holds its options open until we take a closer look. This principle is key to many quantum phenomena and emerging technologies, from the strange interference patterns we discussed earlier to new forms of computation where units of information can represent multiple values simultaneously, processing vast possibilities all at once. Embracing this idea invites us to see the quantum world not as fixed and certain, but as a realm of possibilities, softly balanced in delicate harmony until observed, like a symphony of potential waiting quietly to be heard. Among the many puzzling and fascinating phenomena in the quantum world, one stands out for its mysterious connections. When two particles become linked in a special way, their properties become intertwined such that the state of one instantly influences the state of the other, no matter how far apart they are. This connection persists even if they are separated by vast distances stretching across space. One thoughtful observer famously called this mysterious action at a distance, expressing his discomfort with the idea that information could seem to travel faster than light. Imagine two particles as twins sharing a secret bond. Measure a property of one twin, and you immediately know the corresponding property of the other, even if it is on the other side of the cosmos. This instantaneous connection seems to defy the familiar idea that information can only travel at the speed of light. This phenomenon challenges our intuition about space and time. It reveals a deep underlying unity between particles that transcends ordinary physical separation. Researchers have tested this extensively, confirming that it is a real and fundamental aspect of nature, not an illusion or error. Beyond its mysteries, this phenomenon is the foundation for emerging technologies where the unique links between particles can be harnessed to process and transmit information in entirely new ways, enabling ultra-secure communication and powerful new forms of computation. This strange invisible bond reminds us that the quantum realm operates with rules far different from our everyday world, a realm where distance and separation lose their usual meaning, where particles remain connected in ways that whisper of a deeper unity beneath the surface of all things. The ideas emerging from quantum experiments did not just add details to existing knowledge, they upended the very foundations of how humanity understood reality. Older physics, built on the certainty of fixed laws and the predictability of objects moving in defined paths, suddenly seemed incomplete. Quantum understanding introduced uncertainty, probabilities, and dual natures, showing that at the smallest scales, the world behaves in ways that defy everyday logic. Particles are not tiny solid spheres, but waves of possibility, and measurement itself changes the outcome. This shift challenged the long-held belief that the universe operates like a precise machine with exact, knowable laws. Instead, quantum physics revealed a universe more mysterious, where chance plays a fundamental role and where the act of observation shapes reality itself. The familiar world still holds true for our daily experience, but beneath it lies a subtle probabilistic reality, a layer of existence governed by gentler, stranger rules. This quantum revolution reshaped physics, philosophy, and technology, paving the way for innovations that power modern life. Understanding how these ideas transform science invites us to appreciate the delicate balance between order and uncertainty at the heart of the universe, a balance that is both unsettling and deeply beautiful, like the quiet rhythm of waves on a distant shore. Beneath the familiar layers of atoms lies an even more fundamental realm, composed of tiny entities that form the very essence of matter and energy. These fundamental particles are not made of anything smaller. They represent the most basic building blocks that our understanding has discovered so far. These particles are organized mainly into two families: One family constitutes matter itself, forming the substance of everything we see and touch. The other family acts as carriers for the invisible forces that govern how particles interact, how they attract, repel, and bind together. The matter-forming family includes entities called quarks and another group known as leptons. Quarks are especially important because they combine in small groups to form the particles that cluster together to create atomic nuclei. Without quarks, atoms as we know them would not exist. Leptons, on the other hand, include the negatively charged particles that orbit around nuclei, creating the structure of atoms. There are also ghostly leptons called neutrinos, nearly massless and rarely interacting with matter. They pass through us and the Earth in vast numbers every moment, almost unnoticed, like silent whispers moving through the fabric of space. Each fundamental particle exists in several varieties, each with unique properties that influence how they behave. These subtle differences determine how particles interact and combine to build the diverse matter that makes up everything from dust motes floating in sunlight to distant stars glowing in the night. Opposite to the matter-forming particles, the force-carrying particles mediate the fundamental interactions in the universe. Light particles carry the electromagnetic force, allowing electricity, magnetism, and light itself to exist and propagate through space. These are the particles that bring brightness to our world, carrying energy from the sun to Earth. Other force carriers are responsible for the strong binding force, a powerful connection that holds quarks tightly bound inside the particles that form atomic nuclei, giving these cores their stability. Without this force, the hearts of atoms would not hold together, and matter would not have the structure we observe. Still, other force carriers mediate the subtle transformation force, which governs processes like gradual decay and the fusion reactions that power stars. Among these force carriers, one holds a special place, discovered only recently. It interacts with an invisible field that permeates all space, imparting substance and weight to other particles, making it fundamental to the formation of the universe's structure. All these particles and forces fit within a comprehensive framework, a mathematical and conceptual structure that organizes the particles into families, describing how they interact and combine to build the complex world we experience. This framework has been tested extensively in experiments and has predicted many phenomena with astonishing accuracy. However, this framework is not the final answer. It notably excludes the force that shapes planets, stars, and galaxies, the force of attraction between masses, and cannot explain the mysterious invisible substance thought to comprise most of the universe's mass, yet remaining hidden from our instruments. Researchers continue to search for theories that unify these gaps, hoping to reveal even deeper layers of reality. Despite its limitations, this framework offers a remarkable glimpse into the quiet order underlying the universe's apparent complexity. It shows us how the tiniest particles, governed by subtle forces, come together in intricate harmony to create everything from your own body to distant galaxies. This profound understanding enriches our view of the quantum world, highlighting the delicate balance and structure within all things, seen and unseen. Beneath the particles themselves lies another profound layer of nature's design, the fundamental forces. These invisible threads weave the universe together, governing how matter interacts, moves, and changes. There are four known fundamental forces, each with its own role and reach, each contributing to the tapestry of existence. First is the electromagnetic force, perhaps the most familiar. It controls how charged particles attract or repel each other. This force is behind electricity, magnetism, and light, shaping everything from the glow of a candle to the workings of your own nervous system. It acts over infinite distances, but grows softer with separation, like a whisper fading into silence. Next is the strong binding force, powerful but very short in reach. This force holds quarks tightly bound inside the particles that form atomic nuclei. It also binds these particles together within the atomic core, overcoming the natural repulsion between positively charged entities. Without this force, atoms would not hold together, and matter as we know it would not exist. Then comes the subtle transformation force, responsible for delicate but vital processes like gradual decay and the fusion reactions that power stars. Though its name suggests gentleness, this force plays a crucial role in the life cycle of stars and the creation of elements essential for life. It operates over very short distances, working quietly in the hearts of atoms. Lastly, there is the force of attraction between masses, governing the large-scale structure of the universe. It is the force that shapes the motion of planets, stars, and galaxies. Though the weakest of the four, its influence extends infinitely and accumulates over vast distances, sculpting the cosmos into the majestic structures we observe through telescopes. Together, these four forces form the foundation of physical reality. They govern everything from the tiniest particles dancing in atoms to the grand motions of galaxies swirling through space. Understanding these forces is key to unlocking the secrets of the quantum world and beyond, revealing the invisible architecture that holds all things together. Among the fundamental particles and forces, one discovery stands out for its mysterious and essential role. Often called by a poetic but misleading name, this particle reveals how other particles gain substance and weight, the very property that gives them presence in our world. The story begins with a question. Why do some particles have mass, while others, like the carriers of light, do not? Researchers theorized the existence of a pervasive field filling all space. As particles move through this field, they interact with it to varying degrees. This interaction slows them down and endows them with mass, much like how moving through thick liquid would impede a swimmer's motion. The particle associated with this field is a ripple or excitation within it, an entity that emerged from the field's energy. It was finally observed in recent times, confirming generations of theoretical work and filling a crucial gap in our understanding of particle physics. Without this mechanism, particles would remain massless, moving through space at the speed of light, unable to form atoms, molecules, or the structures that compose stars, planets, and living beings. It is this invisible, subtle presence that makes the material universe possible. The discovery of this particle was a milestone, deepening our understanding of the quantum world's fabric. It reminds us how unseen forces and fields shape reality, working quietly behind the scenes to give form and substance to everything we experience. Beneath the particles we observe in experiments lies a deeper reality, the world of quantum fields. Rather than thinking of particles as tiny, solid objects, modern physics reveals that every type of particle is actually a ripple or gentle disturbance in a corresponding quantum field that fills all of space. Imagine space as a vast invisible ocean with waves rising and falling across its endless surface. Each wave corresponds to a particle, a negatively charged particle here, a carrier of light there, appearing when the field is excited. These fields exist everywhere, even in the emptiest parts of the universe, quietly vibrating and interacting. This idea transforms our understanding of matter and energy. Particles are not isolated points, but manifestations of underlying fields, constantly shifting and fluctuating. Sometimes, particles pop into existence briefly before disappearing, a phenomenon known as gentle fluctuations in the quantum fabric. This framework combines quantum understanding and the physics of motion and energy, providing the basis for our most precise descriptions of particle interactions. It explains how forces are carried by particles like the carriers of light and the binding force, which themselves are ripples in force fields. The fields are interconnected, dancing together in complex ways that give rise to the rich tapestry of particles and forces shaping the universe. Even empty space has energy, sometimes called vacuum energy, which influences cosmic phenomena like the universe's gradual expansion. Understanding quantum fields opens a window into the silent dynamic fabric beneath all matter. It shows that reality is more than solid objects. It is a continuous energetic web of possibilities and interactions, humming gently beneath the surface of everything we know. Even the quiet emptiness of space is never truly empty. According to quantum field theory, the vacuum, what we might think of as nothing, is actually a gently bubbling sea of activity. Tiny, short-lived disturbances constantly appear and vanish, flickering in and out of existence in the briefest of moments. These ephemeral disturbances are not particles in the usual sense. They cannot be directly observed or captured. Instead, they are temporary ripples in quantum fields, born from the uncertainty inherent in the quantum world. Their brief lives and rapid disappearances are allowed by the fundamental principle of uncertainty, which permits certain fluctuations in energy over very short timescales. These vacuum fluctuations contribute to subtle effects measurable in experiments. For example, one effect demonstrates how two thin surfaces placed very close together in a vacuum experience a tiny force pushing them together, caused by the altered distribution of these fleeting disturbances between the surfaces. These temporary ripples also play a vital role in the forces between real particles. They act as intermediaries, popping in and out to carry forces like electromagnetism and the strong binding force. When two charged particles repel or attract, it is as if they exchange a cloud of these temporary carriers, though these carriers never exist long enough to be detected. These ephemeral entities reveal a universe far more dynamic than our everyday experience suggests. The vacuum is alive with hidden energy and restless motion, reminding us that beneath the calm surface of reality lies a gentle, vibrant quantum dance. This strange, invisible activity underpins much of the quantum world, deepening the mystery and wonder of the universe's smallest scales, where even emptiness hums with possibility. Despite the elegance and success of the comprehensive framework organizing fundamental particles and forces, it leaves many deep questions unanswered. Researchers know it is incomplete, like a map that captures familiar landscapes but misses hidden continents waiting to be explored. One of the biggest mysteries is the invisible substance that makes up most of the universe's mass, but cannot be explained by any known particle in the framework. Alongside this mystery, there is an even more puzzling force driving the accelerated expansion of the universe, a phenomenon that challenges our understanding of space, time, and the very fabric of reality itself. Neither of these mysteries fit neatly into the existing framework, hinting at new physics beyond our current theories, layers of understanding yet to be uncovered. Another puzzle lies in the nature of the attraction between masses. Unlike the other fundamental forces, this force resists integration into the quantum world. The framework does not include a quantum theory of this force, and efforts to unify it with the other forces remain incomplete and speculative. Researchers also grapple with why the parameters of the framework, particle masses, force strengths, and more, take the values they do. Are these values fundamental constants of nature, woven into the fabric of existence, or do they vary in unseen ways across the universe, or perhaps across multiple universes? Experiments at particle accelerators continue to search for signs of new particles or forces that could extend the framework. These facilities probe energies and scales that might reveal clues to these deeper mysteries, pushing the boundaries of what we understand. These ongoing questions reflect the vibrant frontier of physics, where the known meets the unknown. They invite us to wonder and imagine as science quietly pushes the boundaries of understanding about the universe's smallest, most fundamental building blocks, seeking to reveal the hidden patterns beneath all that exists. Among the many remarkable quantum phenomena, one stands out where particles pass through barriers that, according to older physics, should be impossible to cross. Imagine a tiny particle approaching a wall that it does not have enough energy to climb over. Instead of bouncing back, the particle sometimes appears on the other side, as if it has slipped right through, like a whisper passing through solid matter. This defies our everyday experience, but is a fundamental aspect of quantum mechanics. At the heart of this phenomenon lies the wave nature of particles. Each particle is described by a wave function which extends beyond physical boundaries. This wave function does not abruptly end at a barrier, but fades gradually, allowing a small probability that the particle can be found on the other side. It is a delicate balance between the particle's energy and the thickness and height of the barrier. The wave gently penetrates the obstacle, and sometimes the particle emerges, having traversed what should have been an impenetrable wall. This phenomenon is not just a theoretical curiosity. It plays a crucial role in many natural and technological processes. In the sun's core, this process allows hydrogen nuclei to overcome their mutual repulsion and merge together, releasing the energy that powers the stars and provides warmth and light to our planet. In everyday technology, this phenomenon underpins the function of devices that image surfaces at the atomic scale by detecting particles that have passed through tiny gaps. It also enables certain electronic components used in high-speed devices and is essential in the operation of memory storage in computers and smartphones, where particles pass through insulating barriers to store information. These applications reveal how the mysterious quantum world quietly shapes the tools we use and the stars we gaze upon. This phenomenon teaches us that nature's rules can be stranger and more fascinating than we imagine, and that tiny particles hold the keys to both cosmic power and advanced technology. The principle of existing in multiple possibilities at once is a core aspect of quantum mechanics that allows particles to exist in a blend of different states simultaneously. Imagine a coin spinning in the air. It is neither heads nor tails, but holds the possibility of being both until it lands. In the quantum world, particles can exist in such a blend of different states, described mathematically by wave functions. This seemingly strange property becomes especially powerful in new forms of computation. Unlike traditional computers, which use units of information represented by either one value or another, quantum devices use quantum units that can be both values at the same time, thanks to this principle of multiple possibilities. This allows a quantum device to process a vast number of possibilities all at once, opening the door to solving complex problems much faster than traditional machines. This principle also leads to quantum parallelism, where calculations are performed simultaneously across many states. This capability could revolutionize fields like secure communication, material science, and optimization, enabling tasks that classical computers would find impossible within any reasonable time. Yet this principle is delicate. It can be disrupted by interactions with the surrounding environment. When a quantum system interacts with the world around it, the multiple possibilities begin to collapse into a single, definite state, a process that gradually erodes the quantum nature of the system. This fragility is one of the biggest challenges in building practical quantum devices that can maintain multiple possibilities long enough to perform useful computations. Researchers work to isolate quantum systems from their environment, using sophisticated techniques to preserve the delicate state of multiple possibilities. This might involve cooling systems to temperatures near absolute stillness, or using clever error correction methods that protect quantum information from disturbances. The ability to harness this principle of multiple possibilities represents one of the most exciting frontiers in modern science and technology, promising transformations in how we process information, secure communications, and understand the fundamental nature of reality itself. Another fascinating quantum phenomenon involves the way identical particles behave in ways that defy our everyday intuition. In the quantum realm, particles of the same type are truly indistinguishable from one another. Unlike everyday objects where each ball or coin has unique features, quantum particles of the same kind are perfectly identical, with no way to tell them apart. This indistinguishability leads to surprising consequences. When two identical particles interact or swap positions, the overall state of the system reflects their fundamental sameness. Depending on the type of particle, swapping two identical particles either leaves the system unchanged or introduces a subtle phase shift, a mathematical signature that has profound physical consequences. This behavior divides particles into two families. One family, which includes particles like the negatively charged ones orbiting atomic nuclei, obeys a principle that prevents two identical particles from occupying the same quantum state simultaneously. This exclusion principle is responsible for the structure of atoms, the way electrons arrange themselves in shells around the nucleus, and ultimately for the diversity of chemical elements and the stability of matter itself. Without this principle, all electrons in an atom would collapse into the lowest energy state, and the rich chemistry that makes life possible would not exist. The exclusion principle gives atoms their size, their structure, and their unique chemical properties. The other family of particles, including the carriers of light, and other force particles, does not obey this exclusion. Instead, many identical particles can occupy the same quantum state, leading to phenomena like the coherent emission of light in certain devices and the formation of special states of matter at extremely low temperatures. Understanding how identical particles behave reveals deep truths about the quantum world, showing that the fundamental sameness of particles at the smallest scales has far-reaching consequences for the structure of matter, the nature of forces, and the possibilities for new states of matter and new technologies. At temperatures approaching absolute stillness, matter can enter extraordinary states that reveal the quantum nature of the world in spectacular ways. When certain atoms are cooled to temperatures just above the lowest possible temperature, they can enter a collective quantum state where thousands or even millions of atoms behave as a single quantum entity. This state was predicted long ago, but only achieved in laboratories in recent times. In this state, the atoms lose their individual identities and merge into a collective wave, all occupying the same quantum state. This creates a form of matter where quantum effects that usually govern only individual atoms become visible on a much larger scale. These exotic states behave in remarkable ways. They can flow without any resistance, like a perfect fluid with no friction. Light passing through them can be slowed to a crawl or even brought to a complete stop and later released. These states offer a window into quantum phenomena that are usually hidden from view, allowing researchers to study quantum mechanics in systems large enough to observe directly. Beyond their scientific interest, these states have practical applications. They are used in extremely precise measurements, in devices that detect the tiniest changes in motion or rotation, and in technologies for quantum information processing. Creating and maintaining these states requires extraordinary precision and control, isolating atoms from all disturbances and cooling them to temperatures colder than anywhere else in the known universe. Yet the effort reveals profound truths about the quantum nature of matter and opens doors to new technologies that harness quantum effects in powerful ways. These exotic states remind us that the quantum world is not just a mathematical abstraction, but a real aspect of nature that can be brought into view under the right conditions, revealing the subtle coherence and unity that underlies all matter. Among the many mysteries of the quantum world, one of the most profound involves how quantum systems transition from the realm of multiple possibilities to the definite reality we observe. This process, often called measurement or observation, lies at the heart of quantum mechanics and raises deep questions about the nature of reality itself. Before measurement, a quantum system exists in a state of multiple possibilities, described by a wave function that encompasses all potential outcomes. When a measurement is made, this wave function collapses, and the system settles into one definite state. The transition from possibility to actuality happens instantaneously, yet the exact mechanism and meaning of this collapse remain subjects of ongoing discussion and interpretation. Some interpretations suggest that the act of observation by a conscious observer plays a role in bringing about the collapse. Others propose that interaction with the environment, even without a conscious observer, causes the wave function to collapse through a process called decoherence, where quantum coherence is lost due to entanglement with the surroundings. Still, other interpretations avoid the collapse altogether, suggesting that all possible outcomes actually occur, each in a different branch of reality. In this view, measurement does not collapse possibilities, but rather splits reality into multiple branches, each experiencing a different outcome. This many worlds perspective offers a way to preserve the linearity of quantum mechanics without invoking collapse, though it raises its own philosophical challenges. Another interpretation emphasizes the role of information and knowledge, suggesting that quantum mechanics is fundamentally about what we can know, rather than about reality itself. In this view, the wave function represents our knowledge of the system, and collapse reflects an update in our information when we make a measurement. These different interpretations all agree on the mathematical predictions of quantum mechanics, which have been confirmed by countless experiments. Yet they offer vastly different pictures of what quantum mechanics tells us about the nature of reality. This diversity of interpretations reflects the profound conceptual challenges posed by quantum phenomena. The question of how quantum systems transition from possibility to actuality touches on deep philosophical issues about the nature of reality, the role of observation, and the relationship between mind and matter. It invites us to contemplate mysteries that go beyond physics into the realm of metaphysics and philosophy, reminding us that even our most successful scientific theories leave fundamental questions unanswered. As we drift deeper into the quantum realm, these questions become softer, more dreamlike, inviting contemplation rather than demanding answers. They remind us that at the heart of the universe lies a mystery, beautiful and elusive, like the boundary between waking and sleep. One of the most intriguing frontiers in modern science involves the interplay between quantum mechanics and the force that shapes the large-scale structure of the universe. While quantum mechanics successfully describes the behavior of particles at the smallest scales, and the theory of space-time curvature describes how masses and energy shape the fabric of space and time. Unifying these two frameworks remains one of the greatest challenges in physics. At everyday scales, and even at the scale of stars and galaxies, the quantum effects are negligible, and the curvature of space-time can be described without reference to quantum mechanics. Similarly, at atomic scales, the effects of space-time curvature are so tiny that they can be safely ignored. But there are realms where both quantum effects and space-time curvature become equally important, such as the centers of certain collapsed stars, or the very first moments after the universe began. In these extreme conditions, neither framework alone is sufficient. Researchers seek a theory that would describe space-time itself in quantum terms, where the fabric of space and time would exhibit quantum properties like uncertainty and superposition. Such a theory would reveal how space-time behaves at the smallest possible scales, distances so tiny that they represent the fundamental graininess of reality itself. Several approaches have been proposed. One envisions the fundamental constituents of reality as tiny vibrating strands rather than point-like particles. In this picture, different vibration patterns of these strands correspond to different particles and forces, including the carriers of the gravitational force. This framework has the potential to unify all forces and particles in a single mathematical structure. Another approach attempts to describe space-time as woven from discrete loops, creating a picture of space as fundamentally granular rather than smooth. This framework focuses specifically on quantizing space-time itself, without necessarily unifying it with the other forces. Other theoretical approaches explore different paths toward unification, each offering unique insights and facing unique challenges. Despite decades of effort, a complete and experimentally confirmed theory remains elusive. The energy scales and distances where quantum gravity effects become important are far beyond the reach of current experiments, making it difficult to test these theories directly. Yet indirect evidence and theoretical consistency provide guidance. Researchers study the predictions these theories make about phenomena that might be observable, such as subtle effects on light from distant cosmic sources or signatures in the cosmic background radiation left over from the universe's earliest moments. The quest to unify quantum mechanics and gravity is not just about completing our understanding of fundamental forces. It touches on the deepest questions about the nature of space, time, and reality itself. It asks whether space-time is fundamental or emerges from something more basic, whether time is continuous or discrete, and what happens to the concepts of space and time at the very boundaries of the universe, or at the hearts of singularities. These questions drift into the realm of the profound and the mysterious, inviting contemplation of the ultimate nature of existence. As we explore these frontiers, the boundaries between science and philosophy blur, and we find ourselves pondering mysteries that have captivated human imagination for generations. Quantum effects are not limited to the realm of atoms and subatomic particles. Increasingly, researchers are discovering that quantum phenomena play important roles in biological systems, in the processes that sustain life itself. This emerging field explores how living organisms might harness quantum effects to perform functions essential to life. One of the most studied examples involves the process by which plants and certain microorganisms capture light energy. During this process, energy absorbed from sunlight is transferred through complex molecular structures with remarkable efficiency. Recent studies suggest that quantum coherence, where energy exists in multiple pathways simultaneously, might help explain this extraordinary efficiency, allowing the energy to explore many routes at once and find the most efficient path. Another intriguing area involves the sense by which certain animals navigate using the Earth's magnetic field. Some birds, for instance, can detect the direction of magnetic fields with remarkable sensitivity. One proposed mechanism involves quantum processes in specialized proteins within the bird's eyes, where the spin states of pairs of particles respond to magnetic fields, providing information about the field's direction. Even the sense of smell might involve quantum effects. One hypothesis suggests that olfactory receptors distinguish between molecules not just by their shape, but by the vibrational frequencies of bonds within the molecules, a process that could involve quantum tunneling. These possibilities are still being investigated, and not all researchers agree on the extent to which quantum effects are essential to these biological processes. The biological environment is warm and wet, conditions that typically destroy quantum coherence very quickly. Yet if living systems have indeed evolved mechanisms to harness or protect quantum effects, it would represent a profound connection between the quantum world and the world of life. The idea that life might exploit quantum phenomena adds a new dimension to our understanding of both biology and quantum mechanics. It suggests that the strange rules of the quantum world are not just abstract curiosities or foundations for technology, but might be woven into the very fabric of living systems, shaping processes from energy capture to perception. As research in this field continues, it invites us to see life itself as a bridge between the quantum and classical worlds, a system that navigates the boundary between possibility and actuality with grace and efficiency honed by countless generations of evolution. These explorations remind us that the quantum world is not separate from our everyday experience, but underlies it, shaping everything from the atoms in our bodies to the processes that sustain life, connecting the smallest scales to the largest, the simplest particles to the most complex living systems. As we drift toward the completion of this gentle journey through the quantum realm, we find ourselves contemplating the profound implications of what we have explored. The quantum world reveals a universe far stranger and more mysterious than everyday experience suggests. It shows us that at the smallest scales, reality is not made of solid, predictable objects, but of waves of possibility, of particles that can be in multiple places at once, of connections that transcend space and time. This quantum nature of reality challenges our intuitions and invites us to reconsider fundamental assumptions about the nature of existence. It tells us that the act of observation plays a role in shaping what we observe, that certainty gives way to probability, and that the universe at its heart is characterized by a gentle uncertainty, a softness that defies the hard determinism of older worldviews. Yet this uncertainty is not chaos. It is governed by precise mathematical laws, by principles that have been tested and confirmed in countless experiments. The quantum world is orderly and predictable in its own way, even as it remains fundamentally probabilistic and mysterious. The journey from ancient philosophical speculations about indivisible atoms to the modern understanding of quantum fields and fundamental particles is a testament to human curiosity and ingenuity. It shows how patient observation, careful experimentation, and bold theoretical thinking can unveil the hidden architecture of reality, layer by layer, revealing ever deeper truths about the nature of existence. As we have seen, the quantum realm is not just an abstract mathematical framework, but the foundation of everything we see and experience. It governs the behavior of atoms, the nature of forces, the structure of matter, and even perhaps the processes of life itself. Technologies that shape modern life, from computers to communication devices, from medical imaging to energy production, all rest on our understanding of quantum mechanics. Yet for all we have learned, profound mysteries remain. The interpretation of quantum mechanics, the unification of quantum theory with gravity, the nature of dark matter and dark energy, the ultimate constituents of reality. These questions await future explorers, inviting new generations to push the boundaries of understanding ever further. As we settle into rest, we can take comfort in knowing that the universe at its smallest scales is a place of profound beauty and mystery. The quantum world is not cold or mechanical, but alive with possibility, shimmering with potential, dancing with the gentle rhythms of uncertainty and probability. This quantum dance underlies all that exists, from the atoms in our bodies to the stars in the sky, from the ground beneath our feet to the air we breathe. We are made of quantum particles, governed by quantum laws, connected to the universe in ways both seen and unseen. As consciousness drifts towards sleep, we can imagine ourselves as part of this vast quantum tapestry, woven from particles and fields, waves and probabilities. We are not separate from the quantum world, but expressions of it, temporary patterns in the endless dance of matter and energy, awareness emerging from the interplay of countless particles, following the subtle rules of quantum mechanics. In sleep, the boundaries between self and universe soften, and we return to a state of pure possibility, not unlike the quantum state before measurement, existing in a gentle superposition of dreams and stillness. The quantum world whispers that reality is more fluid, more mysterious, more beautiful than we ever imagined. And as we drift into sleep, we become one with that mystery, dissolving into the soft uncertainty at the heart of all things. Let the gentle rhythms of the quantum realm carry you softly into the night, into dreams where particles dance and possibilities shimmer, where observation creates reality and consciousness itself is woven from the same quantum threads that bind the universe together. Rest now, cradled in the knowledge that you are part of something vast and beautiful, a quantum system entangled with all of existence, drifting peacefully through the night. The quantum world extends its influence into realms we use every day, shaping technologies that have transformed modern life. From the devices we carry in our pockets to the ways we communicate across vast distances, quantum mechanics underpins the infrastructure of our connected world, working invisibly behind the scenes. One of the most profound applications involves secure communication. The principle that observing a quantum system changes its state provides a foundation for unbreakable codes. When information is encoded in quantum states, any attempt to intercept or eavesdrop on the transmission disturbs these states in detectable ways. This allows communicators to know whether their message has been observed by unwanted listeners, providing security rooted not in mathematical complexity, but in the fundamental laws of nature itself. This quantum approach to security has moved from theoretical possibility to practical reality. Networks using these principles have been established, connecting distant locations with channels that protect sensitive information. Financial institutions, government agencies, and research organizations have begun implementing these systems, recognizing that quantum security offers protection against even the most sophisticated attempts at interception. Another remarkable application involves precision measurement. The quantum properties of particles allow for sensors of extraordinary sensitivity, capable of detecting the tiniest changes in magnetic fields, gravitational pull, or rotational motion. These quantum sensors have applications ranging from medical imaging to navigation, from detecting underground resources to mapping variations in Earth's gravitational field. In medical imaging, quantum principles enable techniques that reveal the inner workings of the human body without invasive procedures. These methods rely on the quantum behavior of atomic nuclei, which respond to magnetic fields in ways that can be measured and translated into detailed images of soft tissues, organs, and even the activity of the brain itself. The principle of multiple possibilities also promises to revolutionize computation. While traditional computing processes information step by step, quantum devices could explore many computational paths simultaneously, leveraging superposition to tackle problems that would take conventional computers longer than the age of the universe to solve. Though still in early stages, these devices have begun to demonstrate capabilities beyond classical machines for certain specialized tasks. Researchers continue to refine these quantum technologies, overcoming challenges related to maintaining delicate quantum states in noisy, warm environments. Each advance brings us closer to harnessing the full potential of quantum mechanics, transforming abstract principles into practical tools that enhance our ability to communicate, compute, measure, and understand the world around us. These applications remind us that the quantum world is not merely an abstract realm studied by specialists, but a foundation for technologies that touch our daily lives, connecting us, protecting our information, healing our bodies, and expanding our capabilities in ways that earlier generations could scarcely have imagined. As we explore the quantum realm, we encounter not only scientific principles, but philosophical questions that have puzzled thinkers for generations. What is the nature of reality? Does the universe exist independently of observation? Or does consciousness play a role in bringing reality into being? These questions, once the domain of philosophers alone, have been brought into sharp focus by the discoveries of quantum mechanics. The traditional view held that the world exists in a definite state. Whether or not anyone observes it, objects have properties, position, velocity, color, mass, that exist independently of measurement. The role of the scientist was simply to uncover these pre-existing properties through careful observation and experiment. Quantum mechanics challenges this view. It suggests that before measurement, systems do not possess definite properties, but exist in states of possibility. The properties we measure, the position of a particle, the spin of an atom, do not pre-exist the measurement, but emerge through the act of observation itself. This implies a profound interconnection between observer and observed, between consciousness and physical reality. Some interpretations take this further, suggesting that consciousness itself plays a fundamental role in collapsing the wave function, in selecting one possibility from the many that exist in superposition. In this view, mind and matter are not separate, but intimately connected, with awareness serving as the bridge between potential and actual. Other interpretations avoid placing consciousness in such a central role, attributing the collapse to interaction with the environment, or proposing that all possibilities are realized in parallel universes. Yet the question remains, what does quantum mechanics tell us about the nature of reality itself? These philosophical implications extend to questions of determinism and free will. In the older mechanical worldview, the universe operated like clockwork. If you knew the position and velocity of every particle at one moment, you could, in principle, predict the entire future of the universe. There was no room for genuine randomness, no space for free will beyond the illusion created by our ignorance of initial conditions. Quantum mechanics introduces genuine randomness into the fabric of reality. The outcome of a quantum measurement is not determined by hidden variables or initial conditions, but is fundamentally probabilistic. This suggests that the future is not fixed, that the universe genuinely creates itself moment by moment through a process that involves an element of chance. Does this quantum randomness create space for free will? The question remains open, inviting contemplation. Some argue that random quantum events in the brain could influence neural processes, providing a mechanism for choices that are neither determined by prior causes nor simply random, but emerge from the interplay of consciousness, quantum uncertainty, and neural complexity. Others maintain that quantum randomness alone does not solve the problem of free will, that truly free choices require something more than mere chance. These debates continue, reminding us that even our most successful scientific theories leave fundamental questions about agency, choice, and the nature of consciousness unresolved. The quantum world also invites us to reconsider the nature of time itself. In everyday experience, time flows from past to future in an unchanging direction. We remember the past, but not the future. Causes precede their effects. Yet quantum mechanics, in its mathematical formulation, treats time symmetrically. The equations work equally well running forward or backward in time. This temporal symmetry contrasts with our lived experience of time's arrow. Why do we experience time as flowing in one direction? The answer seems to lie in the increase of entropy, the tendency of systems to become more disordered over time. Yet the connection between quantum mechanics, entropy, and the arrow of time remains a subject of ongoing investigation. Some interpretations of quantum mechanics suggest that the act of measurement, the collapse of the wave function, introduces an arrow of time into the quantum world. Before measurement, quantum systems evolve reversibly, able to run backward as easily as forward. But the irreversible act of measurement, where possibilities collapse into actuality, marks a direction in time. These deep questions about reality, consciousness, free will, and time invite us into a space of wonder and mystery. They remind us that science is not just about accumulating facts, but about grappling with fundamental questions that have occupied human minds since we first looked up at the stars and asked why. As we contemplate these mysteries, the boundaries between physics and philosophy dissolve. We find ourselves in territory where experimental results and mathematical formalism meet questions of meaning, purpose, and the nature of existence itself. It is a space that invites not just intellectual analysis, but a kind of meditative contemplation, a quiet wondering about the ultimate nature of all that is. The quantum realm teaches us humility. Despite our sophisticated theories and powerful instruments, we remain in the presence of mystery. The universe reveals itself as stranger, more subtle, more beautiful than we ever imagined. At the smallest scales, reality shimmers with uncertainty, dances with possibility, and whispers secrets that we are only beginning to hear. This uncertainty is not a defect or limitation, but a fundamental feature of existence. It tells us that the universe is not a dead mechanism, but something alive with potential, constantly creating itself moment by moment through processes that blend law and chance, determinism and spontaneity in ways that defy simple understanding. As we rest in this space of not knowing, of gentle uncertainty, we find a strange kind of peace. The quantum world invites us to release our grip on certainty, to embrace the mystery at the heart of existence, to find comfort in knowing that reality is more vast, more mysterious, more wonderful than any fixed view could capture. Let these thoughts drift through your consciousness like particles in superposition, neither fully grasped nor completely released, but held lightly, softly, in the gentle space between knowing and unknowing. The quantum world is a mirror reflecting back to us our deepest questions about existence, offering not final answers, but an invitation to wonder, to contemplate, to rest in the beautiful mystery of being. In quantum mechanics, we encounter a description of nature that works, that predicts experimental outcomes with stunning accuracy, yet defies easy interpretation. This is a profound lesson. Reality does not owe us an explanation we can easily visualize or comprehend. The universe operates according to its own principles, which we glimpse through mathematics and experiment, but may never fully grasp through intuition alone. This teaches us to hold our models of reality lightly, to recognize that our theories are maps, not the territory itself. They guide us, help us navigate, allow us to make predictions and build technologies. But the map is never the landscape. The equations are never the reality they describe. Something always escapes. Something remains beyond capture. This perspective cultivates a kind of intellectual humility and wonder. We are participants in a vast cosmos that extends beyond our understanding, creatures of limited perception trying to comprehend the infinite. Yet in that very limitation lies a profound beauty. The fact that we can understand anything at all about the quantum realm, that we can harness its principles for practical purposes, speaks to a deep connection between mind and nature, between consciousness and cosmos. The quantum world shows us that reality is participatory. We are not separate observers standing outside nature, looking in. We are part of the system we observe, entangled with it through the very act of measurement and observation. The boundary between subject and object softens and blurs. We discover ourselves woven into the fabric of existence in ways both profound and mysterious. This participatory view invites a different relationship with nature, one less about control and domination, and more about dialogue and co-creation. When we measure a quantum system, we are not merely uncovering pre-existing facts, but participating in the actualization of possibilities. We are partners in the ongoing creation of reality. These insights extend beyond physics into ethics and spirituality. If we are truly entangled with all of existence, if the boundaries between self and other are less fixed than we imagine, then how we treat the world becomes how we treat ourselves. The quantum vision of interconnection echoes ancient wisdom traditions that speak of the fundamental unity of all things. As we float in this space of quantum contemplation, boundaries dissolve. The separation between observer and observed, between mind and matter, between self and universe, becomes less certain. We glimpse a deeper unity, a wholeness that underlies the apparent multiplicity of separate things and beings. This unity is not sameness, but a kind of coherent diversity, like the interference patterns created when quantum waves overlap. Individual identities remain, yet they are woven together in patterns of connection and correlation, creating a tapestry richer than any single thread could be alone. In this vision, consciousness itself appears not as an isolated phenomenon, but as something woven into the fabric of the universe from the beginning. Perhaps awareness is not something that emerges only in complex brains, but exists in some proto-form throughout nature, a fundamental aspect of reality alongside matter and energy. These speculations drift beyond what current science can confirm or deny. They represent the frontier where scientific understanding meets philosophical imagination, where verified knowledge fades into inspired vision, yet they emerge naturally from contemplating the strange truths revealed by quantum mechanics, inviting us to expand our conception of what is possible, what is real, As consciousness begins to drift towards sleep, these thoughts become softer, more dreamlike. The quantum realm and the realm of dreams share a certain quality. Both are spaces where normal rules suspend, where things can be in multiple states, where the observer affects what is observed, where past and future blur into an eternal present. In sleep, we release our attachment to definite positions, fixed identities, clear boundaries. We enter a state of pure possibility, not unlike the quantum superposition that exists before measurement. Dreams mix and blend elements from memory and imagination, creating scenarios that defy waking logic, yet possess their own internal coherence, much like quantum phenomena that defy classical logic yet follow their own mathematical laws. The transition from waking to sleeping mirrors, the quantum transition from definite to indefinite, from actual to potential. As we drift off, we return to a more fluid state, where the boundaries we maintain during waking life soften and dissolve, where we become once again part of the undifferentiated whole from which we emerge each morning. This nightly dissolution and re-emergence echoes the quantum process of decoherence and recoherence, the constant dance between definiteness and possibility that underlies all existence. We are quantum beings, participating in this dance at every level of our being, from the particles in our atoms to the neural processes that generate consciousness itself. Rest now in this understanding. You are a quantum system, a collection of particles governed by probabilities and uncertainties, yet somehow giving rise to the definite experience of being you. This mystery of how quantum possibility becomes classical experience, how probability becomes actuality, how the many become one, is the mystery of your own existence, played out in every moment. As sleep deepens, let go of the need to understand. Let the quantum mysteries wash over you like gentle waves, carrying you into dreams where all things are possible, where you exist in superposition of countless scenarios, exploring infinite possibilities in the space of sleep. The quantum world has shown us that at the deepest level, reality is made not of things, but of possibilities, not of certainties, but of probabilities, not of separations, but of connections. As you drift into sleep, become those possibilities, those probabilities, those connections. Dissolve into the quantum field from which all things arise and to which all things return. Let the gentle uncertainty at the heart of existence cradle you softly into the night, into dreams, into the peaceful darkness where all distinctions fade and only the soft glow of pure potential remains, waiting quietly for the dawn when once again possibility will collapse into the definite experience of awakening, of being, of life. As we reach the gentle conclusion of this journey through the quantum realm, we find ourselves floating in a space between waking and dreaming, between knowing and wonder, between the definite world of everyday experience and the soft, uncertain realm of quantum possibility. Throughout this journey, we have explored the hidden architecture of reality, from the ancient dreams of indivisible atoms to the modern understanding of quantum fields and fundamental particles. We have seen how the solid world dissolves into mostly empty space, how particles dance as waves of possibility, how observation itself shapes what we observe. The quantum world has revealed itself as a realm of profound beauty and mystery. At the smallest scales, nothing is fixed or certain. Particles exist in clouds of probability, in states of superposition where multiple possibilities coexist until the moment of measurement. This is not chaos, but a different kind of order, one based on probabilities rather than certainties, on relationships rather than isolated objects. We have witnessed the strange phenomenon where particles can be entangled across vast distances, remaining connected in ways that transcend space itself. We have explored how particles can tunnel through barriers, how identical particles behave according to principles that give rise to the structure of atoms and the diversity of matter. We have seen how, at extremely low temperatures, matter can enter collective quantum states that reveal the quantum nature of reality on scales large enough to observe directly. The quantum realm has shown us that reality is participatory. We are not separate observers looking at a pre-existing world, but participants in the ongoing creation of reality. Through the act of observation, we help bring definite outcomes into being from the realm of pure possibility. This insight connects us intimately to the fabric of existence, showing that consciousness and matter are intertwined in ways deeper than we ever imagined. These discoveries have profound implications, not just for physics, but for philosophy, for our understanding of consciousness, free will, and the nature of time itself. They invite us to release old certainties and embrace a more fluid, more mysterious vision of reality. The universe is not a clockwork mechanism, but something alive with possibility, creating itself moment by moment through processes that blend law and chance. As we rest in this understanding, we can appreciate how quantum mechanics has transformed not just our theories, but our technologies. From the devices we use to communicate to the methods we use to heal, from secure communication networks to powerful sensors, the principles of quantum mechanics shape the tools of modern life. Yet the quantum world remains profoundly mysterious, inviting continued exploration and wonder. Let us now allow all these concepts, all these facts and principles to dissolve into a softer space. There is no need to hold on to them, to remember every detail. Let them flow through your consciousness like water, leaving behind only a gentle sense of wonder, a quiet appreciation for the profound mystery at the heart of existence. Imagine yourself as a quantum system, a collection of particles held together by invisible forces, animated by fields that extend throughout all space. You are not separate from the quantum world, but an expression of it, a temporary pattern in the endless dance of matter and energy. Every atom in your body was forged in the heart of ancient stars, scattered through space, and gathered together to form you. You are literally made of stardust, of quantum particles that have existed since the earliest moments of the universe. As you breathe, quantum processes unfold in every cell of your body. Electrons tunnel through barriers in your metabolism. Quantum coherence may play a role in how your eyes capture light, how your nose detects scents, how energy moves through the molecular machinery of life. You are a quantum being, through and through, yet you are also more than the sum of your particles. Somehow, from the interactions of countless quantum entities following probabilistic laws, emerges the definite experience of being you. This is perhaps the deepest quantum mystery of all. How possibility becomes actuality, how the many become one, how quantum processes give rise to classical experience and conscious awareness. As sleep approaches, this mystery deepens. The boundary between waking and sleeping mirrors the quantum boundary between definite and indefinite, between measured and unmeasured, between actual and potential. In sleep, you release the fixed sense of self maintained during waking hours. You enter a more fluid state where identities blur, where time becomes less linear, where the impossible becomes possible. Dreams are like quantum states, holding contradictions without conflict, exploring possibilities without commitment. In dreams, you can be in multiple places, multiple times, multiple identities. The dream world operates by its own logic, one that resembles quantum logic more than classical logic. Perhaps in dreaming, we reconnect with the quantum nature that underlies all existence, a realm of pure potential that the waking mind normally constrains into definite forms. Let yourself drift now toward that dream realm. Release your grip on the definite world. Allow the boundaries you maintain to soften and dissolve. You are safe to let go, to surrender to the quantum uncertainty at the heart of being. In sleep, you return to a more fundamental state, a state of pure potential from which each morning you will emerge renewed. Feel your body becoming lighter, less solid, more like a cloud of particles held together by gentle forces. The atoms in your body are mostly empty space, and even the particles themselves are better understood as waves, as ripples in quantum fields that extend throughout all existence. You are not separate from the universe, but continuous with it, woven into the fabric of reality at every level. As your breathing slows and deepens, imagine each breath as a wave function, expanding on the inhale, collapsing on the exhale. With each breath, you participate in the quantum dance, exchanging particles with the air around you, with the universe itself. Oxygen molecules that were once part of distant forests, ancient oceans, other living beings, now become part of you, carrying out the quantum processes that sustain your life. Let go now of the need to understand, to analyze, to grasp. The quantum world teaches us that some things cannot be visualized or fully comprehended through everyday concepts. There is a limit to what can be known, what can be pinned down. This limit is not a failure, but a fundamental feature of reality. It invites us to rest in mystery, to be comfortable with not knowing, to find peace in uncertainty. The universe, at its deepest level, is made of possibilities, not things. As you drift towards sleep, you return to that level, becoming pure possibility yourself. In the space of sleep, you exist in superposition, exploring countless scenarios, countless versions of reality, free from the constraints that collapse possibilities into single outcomes during waking life. Imagine yourself dissolving into the quantum field, becoming one with the ocean of possibility from which all things arise. You are a wave in this ocean, distinct yet not separate, individual yet part of the whole. The wave rises and falls, appears and disappears, yet the ocean remains, eternal and unchanging. In this vast quantum ocean, there is no separation, no isolation. All particles are connected through subtle correlations, entangled in ways that transcend space and time. You are connected to everything, to every atom in the universe, through invisible threads woven into the fabric of reality itself. In sleep, you may sense this connection more deeply, as the boundaries of the individual self become less rigid. Rest now in this vision of unity and connection. You are held safely in the quantum field, cradled by the same forces that hold atoms together, that guide stars in their courses, that shape galaxies across the cosmos. These forces are gentle yet powerful, invisible yet present everywhere. working silently to maintain the delicate balance of existence. As consciousness fades towards sleep, notice how thoughts become less distinct, how the sharp boundaries between concepts soften and blur. This is like quantum decoherence in reverse. Instead of possibilities collapsing into definite states, definite thoughts dissolve back into the undifferentiated field of potential from which they emerged. You are returning to the source, the quantum ground of being. Let the last vestiges of waking consciousness drift away, like morning mist dissolving in sunlight. There is nothing you need to do, nowhere you need to be, nothing you need to accomplish. In this moment, you are complete, perfect, whole. You are a quantum system in a state of rest, energy distributed evenly, all possibilities held in gentle equilibrium. The quantum world whispers its final secret, that beneath all complexity is simplicity, beneath all separation is unity, beneath all certainty is the soft glow of possibility. Rest now in this simplicity, this unity, this gentle, uncertain ground of all being. Sleep comes not as an ending, but as a return to the source, a dissolution into the quantum field from which you will emerge tomorrow, renewed and refreshed. Let your last waking thoughts be of gratitude for the quantum processes that sustain your life, for the ancient stars that forged your atoms, for the mysterious forces that hold you together and connect you to all things. You are a miracle of quantum mechanics, a temporary pattern of incredible complexity and beauty arising from the interplay of simple rules and chance events. As you slip into sleep, imagine the quantum field itself breathing, pulsing gently with the rhythm of your own breath. You and the universe breathe together, bound in the same dance, made of the same fundamental stuff, expressions of the same underlying reality. In sleep, the illusion of separation falls away completely, and you rest in the truth of your deep connection to all that is. Sleep now, quantum traveler. Rest in the soft uncertainty. Dissolve into the field of pure potential. Let go of all definitions, all boundaries, all attempts to grasp or hold. Simply be, not this or that, but pure possibility itself, waiting in the quiet darkness for the dawn when once again the wave function will collapse, and you will emerge into the definite world of waking life, carrying within you the memory of this quantum peace, this deep rest in the heart of mystery. Good night, fellow quantum system. May your dreams dance with particles and waves. May your sleep be deep and renewing. May you rest in the knowledge that you are held always in the quantum field, connected to everything, part of the great cosmic whole, a precious expression of the universe contemplating itself. Drift now, dissolve, let go, and sleep